This is the second in the series of 3 videos on the topic agonist efficiency. In the first video, I talked about the basics of receptor operation. In this video, I'm going to talk about efficiency per se. Efficiency is the correlation between agonist affinity and agonist efficacy. And in the third video, I'm going to talk about the energy linkage that undergird this correlation. So the topics of this video are the definition of efficiency, how do you measure it, what are some of its features, what are structural correlates, and how can it be applied to dose response analysis. The efficiency of a machine is symbolized by the Greek letter eta, is equal to the energy out divided by the energy in. Receptors are molecular machines, where the energy out is the gating energy or the response energy, and the energy in is the binding energy. So agonist efficiency is the fraction of binding energy converted into gating energy. So what are these two energies? What is the efficiency of an agonist? Let's start with the numerator, the energy out. We know from the thermodynamic cycle that the ratio of gating energies, equilibrium constants, is equal to the ratio of binding equilibrium constants. Where KDC is the low affinity binding constant and KDO is the high affinity equilibrium dissociation constant. Energy is minus the log of an equilibrium constant, so the minus the log of this ratio, known as the coupling constant, is equal to this numerator. And the binding to the binding energy is the maximum that you can get out of the ligand, which is related to KDO. It's actually 1 over KDO. So minus the log of 1 over KDO is just the log of KDO. So this is the efficiency of an agonist. It's only a function of the equilibrium dissociation constants, and it can be simplified into this form. And this should be a familiar form to those who are familiar with heat engines or the Carnot cycle, because it is the same form as the equation given for a steam engine by these two fellows, Sadi Carnot and Lord Kelvin, about 200 years ago. But instead of the binding energy ratio to the right there, it was the temperature ratio. The efficiency of a steam engine is 1 minus T hot minus T, 1 hot divided by T cold. So for a agonist, all you have to do to measure its efficiency is to measure those two equilibrium dissociation constants. And that can be done any number of ways. In the first video, I showed you how it could be done by direct measurements using single channels. And I also showed how these two constants can be derived from a dose response curve. But it's also possible to measure these constants biochemically just by measuring in a binding assay. If you have enough C protein, and you can measure the affinity of the ligand as long as you can keep the receptor in C, and you can do that by making the L0 very small. And similarly with O, if you had a bucket of O protein and you could keep it in O, or maybe have it desensitized to the same affinity, desensitized, which has the same affinity of O, you can measure these two constants and calculate the affinity. And I think in the long run, using biochemistry could be the quickest way and most widely used ways to measure efficiencies. But right now, I'm going to do it from dose response curves, as I described in the first video. So let's look at dose response curves. These are from mouse muscle adult type acetylcholine receptors activated by these 3 different agonists: acetylcholine, epibadidine, and tetramethylammonium. And just with an eye towards efficiency now, if you call the x-axis the energy in and the y-axis is something related to the energy out, you can see that with the comparing ACH and epibadidine, the black and the red, they have similar energy in, but ACH has a much larger energy out. So you would say ACH has the higher efficiency compared to epibadidine. It's a little more difficult to say what's going on between ACH and TMA. But let's do the quantitation. So we fit the points to a Hill equation to get a maximum value and an EC50 value from which we calculate the gating equilibrium constant L2, and then the two equilibrium dissociation constants, which is what we want to get affinity. So the low affinity constants in the micromolar range, the high affinity constants in the nanomolar range. So if you take log of 174 times 10 to the minus 6 molar divided by log of 30 times 10 to the minus 9th molar, and you calculate that ratio, and 1 minus that ratio, multiply it by 100% to turn it into a percentage, and we get the following numbers. Acetylcholine is 50% efficient and more efficient than epibadidine. So only 42% of epibadidine's binding energy goes towards gating, whereas fully half of ACH receptors, acetylcholine's binding energy goes towards gating. And PMA is even more efficient than ACH. So it's fine to know these numbers. So you can get an efficiency from any agonist on any receptor. These responses are single channel open probabilities, and some receptors are more difficult to get that number. So we also got these using whole cell current measurements using an ion flux machine. So that's shown in the top panel here is the ion flux dose response curves, and the single channel open probability dose response curves that I showed previously are repeated here at the bottom. And you can see in the whole cell measurements, the efficiencies are slightly lower than they are in the single channel measurements, but the relative efficiencies of the three agonists remains the same. And the reason they're lower is because of desensitization. In the single channel data, all desensitization has been removed from the accounting. So we are just talking about binding and gating in the bottom panel. In the top panel, the perfusion time was about 200 milliseconds, and there was some desensitization. These values are normalized to the star, the asterisk shown above at 300 micromolar ACH. All of the currents were normalized to that value. And there is some desensitization, as you can see. In the ACH figure, as you go to higher concentrations, the response gets smaller. That's due to desensitization. So there's a few percent reduction in the efficiency because of desensitization when you do not remove it from the accounting. But we're going to stick with the more accurate method, the single channel open probability method. It may not be generally applicable, but it is applicable in nicotinic muscle type receptors, so we're going to go with the better way to measure it. So as I said, any agonist on any receptor can give you an efficiency, and it's nice to know that you could quantify these efficiencies for the different agonists, but that's not what makes efficiency interesting. What makes efficiency interesting is that many agonists have the same efficiency. So this is a plot of the two equilibrium dissociation constants plotted against each other in log-log format. And each symbol is a different agonist. So each symbol represents an entire dose response curve of a single agonist, from which both KDC and KDO were calculated using a known value of L0. This was done by Snail Jady back in 2012, a graduate student in my lab. So when we first saw this, we were astounded because we knew that the binding to O was going to be higher affinity than to C, but we did not know that there would be such a uniform relationship to so many different ligands, and that the binding energy would double. What the slope of 0.5 means is that the binding energy to C is half of that to O. And that energy doubles when the protein goes from C to O, and it doubles regardless of the affinity of the ligand. That's given on the y-axis as the log of the KDC, and also independent of the efficacy of the ligand. So the rightmost point is for acetylcholine, which has a maximum of 0.96 PO, and choline, on the other hand, is a very weak agonist, only 0.05 is the maximum that you get out of choline. So regardless of energy of affinity or efficacy, the binding energy doubles. And this was a big puzzle to us. And We didn't understand what this meant at the time, but now we know what that slope of that line means. The slope of that line is the right hand is the ratio in the equation for efficiency. So the fact that all of these points fall on that line means that all of these ligands have the same efficiency. We can take the analysis one step further by combining that efficiency equation with the green equation that was derived from the thermodynamic cycle, and that results in this blue equation, which is that of a straight line. So log ln is equal to y is equal to mx plus b, where y is log n and x is equal to log 1 by kd. So that's a straight line. M, the slope, is related to efficiency, as shown below. It's equal to efficiency is equal to the slope divided by the slope plus n, where n is the number of binding sites, which you know a priori. So if you can make this plot and calculate, fit it to a straight line and calculate a slope, you can easily calculate the efficiency. And we have done this for 20 different agonists of the acetylcholine receptor using dose-response curves or single-channel measurements. So these are for the 9 agonists shown to the right are plotted in the form of this equation, where y is equal to the log of the diligand gating equilibrium constant, and x is equal to the log of the inverse of the KDC. And you can see they all fall on the same line. Again, each point is an entire dose response curve. So all of these agonists fall on the same line. There's 2 of them here. We did this for 2 sites independently. That's why there's so many points here. But all of the agonists to the right have the same efficiency, which is 51%. That's from the slope of that line. So the same efficiency applies to agonists having different scaffolds. So acetylcholine, nicotine, and DMPP all have different scaffolds, but they have the same, they all fall on the same line. They all have a 51% efficiency, as do the other agonists listed below. And this plot also shows that efficacy and affinity, the correlation between the two, it takes place over a wide range. So the x-axis here is energy in, that's affinity, and the y-axis here is energy out, that's efficacy. So over several orders of magnitude in each, the correlation holds for these 9 different agonists. So these are 9 agonists. Here's 10 more that were plotted on this plot. We plotted 7 that were related to epibadidine, and they all fell on a slope of a plot that had a slope of 42%, as we saw for the individual agonist from the individual dose response curve. And 3 of them, PMA, DMP, and DMT, fell on a different line, which had the slope of 54%. Now these 3 lines were fitted independently, and they all project to the same L0, as you would expect if L0 was the unliganded equilibrium constant. And that value of L0 is the same as estimated by other methods described in the first video lecture. So we can conclude from this plot that the efficiency values are discrete and precise. Discrete meaning they're not just scattered all over the place. They fall on one of 3 lines for 19 different agonists, and that L0 can be estimated from the y-intercept. So if you make a plot for, let's say, even to 3 green agonists and just extrapolate to the value where log 1 by KDC is equal to 0, you can get L0. So this is a good way to get L0 from wild-type receptors. You don't have to know anything in advance. These are 2 easily measured things from the dose-response curve, KDC and L2. You don't need L0. It comes out of the analysis, as long as you have several agonists that have the same efficiency. So that's 19 agonists. I told you we did 20. So this was the 20th. It was an outlier. Varenicline, which is a smoking cessation drug known as Chantrix, did not fall on either of those 3 lines. It was off the curve. And when we use the same L0, we calculate that agonist has an efficiency of 35%. And of course, we would like to study more agonists that are related to varenicline, but we couldn't find any online. So what I want to point out here with these 20 agonists is that the correlation between efficacy and affinity is apparent only when agonists are segregated by efficiency. So the two boxes highlight this. The vertical box shows 3 agonists that have the same similar affinities. They fall on the same point on the x-axis. And the horizontal box shows 3 agonists that have the same efficacies. They fall at the same point on the vertical axis, on the y-axis. And if you didn't know that they belong to different efficiency families, you would come to the conclusion that there is no correlation between efficacy and affinity. So if you just picked 5 of these points and didn't worry about the color, and you just randomly pick 5 or 6 points and put them on this plot, you would, and that's 5 or 6 dose response curves. So every point here is an entire dose response curve. If you did 5 or 6 ligands, did dose response curves, and plotted affinity versus efficacy on a log-log scale, you would come to the conclusion that there is no correlation between affinity and efficacy. You only see it, one, when you have a lot of data, a lot of points, and 2, when you have agonists from multiple agonists that come from the same family, but you will see that there are different efficiency families. So agonists can be classified according to efficiency. So right now they are classified by affinity and efficacy. I think efficiency is a new classification scheme that is ultimately going to be very useful. What about other receptors? Well, we didn't do these experiments. These experiments came from literature values, and the literature, the papers that they were drawn from are given in the citation shown at the bottom of this slide. What we did was we plotted the values of equilibrium dissociation constant affinity in log form, turned it into an energy by taking the minus logarithm of it, and the efficacy from the maximum P open. We identified outliers in the curve statistically. So we gradually removed points until the R value, the correlation coefficient, stopped changing by some threshold amount. So, for example, the GABA A receptors, a lot of agonists were examined, and 2 stood out as not fitting with the other ones. So we only fit the blue lines to get efficiency. So we calculated efficiency from the slope of the blue lines. And you can see for all of these agonists, they're in the range of the efficiencies that we found for ACH receptors, 39% to 59%. 59% is a little higher, but the error limits on these are fairly large. I want to discuss for a moment the M3 muscarinic receptor for several reasons. One is that it's a GPCR, so the coupling between the agonist binding and the response is more downstream than it is in a ion channel, where the conformation change of the receptor and the ion flow are very closely coupled. But apparently you can still get efficiency even though the coupling is a little bit further downstream. And the efficiency was the same as what we had in the nicotinic receptor. The 2 outliers were oxytremerine and pilocarpine, which were structurally distinct. And I'll get into the structural basis of what's determining efficiency. So even in this paper, the authors use this plot to say that there is no correlation between affinity and efficacy. I would tend to think that perhaps that there is a different, the 2 red ligands belong to a different efficiency family, and there is a correlation within a structure related group of agonists, such as those 4 shown below. So these results suggest that the correlation between affinity and efficacy may pertain to other receptors. So now I'm going to get into a little more of the features and structures of the efficiency in nicotinic receptors. So this is a close-up of a nicotinic receptor neurotransmitter binding site. And in all nicotinic receptors, the agonist is surrounded by a cluster of 5 aromatic residues. In adult type receptors, 3 of these provide the lion's share of binding energy. And the actual breakdown from each residue and each actually functional group in each residue is shown in the references shown below. But the main contributor is Y190, in which both the aromatic ring and the hydroxyl group contribute equally to stabilization of the ligand. And I also want to point out there's a glycine near the binding site that we studied as well. So we studied all of these aromatics. We did not study the tryptophan on the complementary on the right there, the other subunit, because it is not a contributor in adult type receptors, although it is a strong contributor in fetal type receptors. So the first thing we noticed about efficiency and structure is that there seemed to be a correlation between agonist size and efficiency. So the small ligands like tetramethylammonium and DMP shown here, the green ligands, have a higher efficiency than varenicline, which has the biggest of the ligands we studied. So this is a plot of the measured efficiency versus the volume of the agonist head group, and it's a little tricky to define head group, but that we just took the first bond away from the tetramethylammonium group, for example, in the black group, and you could see that there is sort of a correlation between size and head group volume. It's not a beautiful correlation. There are other factors in play here, but there seems to be that large agonists have lower efficiencies. That's one feature in adult type nicotinic receptors. So let's look at the binding site now. We also calculated the volume of the binding pocket after docking in different agonists into homology models of the closed and open forms of the binding site. We also did this with full-length PDB files, but also with homology models of just the extracellular domain. And the results were similar in both cases, that the O binding pocket is smaller than the C binding pocket, with, let's look at ACH in there, by about 25% or so smaller, and with ACH. And however, the extent of the reduction in the pocket volume was less with lower efficiency ligands. The binding pocket, by the way, was calculated by connecting the centroids of all the aromatic residues and calculating the volume of the pyramid that is formed by those centroids. So the right shows the summary of the results for all the ligands we studied. We studied 3 different 51% ligands at 2 different kinds of binding site, alpha epsilon and alpha delta. Those are the 6 bars, the 6 black bars. And then we studied 4 ligands at the 42% ligands, efficiency ligands at the alpha delta site. So you can see that the closed cavity volume was approximately the same for both higher 51% efficient and 42% efficient ligands. I'll call those high and low efficiency ligands. So the starting C volume was approximately the same for both. However, the O volume was significantly, the contraction of the binding pocket was significantly greater for the higher efficiency ligands compared to the lower efficiency ligands. So the higher efficiency ligands, and now we're adding the 54% TMA ligands in here, which is why there's more bars. They contracted approximately 25%, and the 42% ligand binding pocket contracted only by about 12%. So the shrinkage of the pocket is greater with the higher efficiency ligand group. So that led us to the following hypothesis: why do larger agonists have lower efficiencies? In C to O, there is a contraction of the binding cavity that is limited by van der Waals contact with the agonists. So this in turn limits the energy transfer to the next structural elements in the gating process. So this idea is that the binding pocket wants to collapse when it goes from C to O to a discrete high affinity conformation, But when there's a large ligand in the binding pocket, it is frustrated by van der Waals contact, and it cannot make that full transition. And as a result, the energy that's transferred to the next structural elements, whatever they may be, is less when there's a low efficiency ligand in there. This is why you get less energy for gating with low efficiency ligands compared to high efficiency ligands. This is a hypothesis that can be tested by both structure and electrodynamic simulations, but it's consistent with what we have done so far. So efficiency also depends on the composition of the binding site. So here I'm going to be next two histograms. I'm going to show you the effects of mutations. This histogram is effect of 44 different mutations of the aromatic residues. Those three aromatic residues: Y190, Y198, Y149, as well as a fourth Y93, which is not a big contributor to binding, but it is in here. And you can see, and for each of these, we had to measure L0. When you make a mutation, the unliganded gating equilibrium constant might change. So we measured L0 for each one of these in order to calculate the efficiency. And you can see that for most of the mutations didn't do much to the ACH efficiency. These are all with using ACH as the agonist. In wild-type receptors, the arrow shows it's 51% efficient in wild-type, and the results of most of the mutations were 51% efficient. However, there were a few mutations that increased the efficiency to 55%, and those mutations were mainly of the W149 tryptophan. So efficiency goes up when you don't have to move that big bulky tryptophan around. And one mutation, the Y190A of that very important Y190 residue, lowered the efficiency to 35%. So that was the distribution of about 44 different mutations in terms of efficiency. We also measured the efficiency for 16 different combinations of side chain and agonist of the receptor of the binding site residue G153, that glycine I pointed out. So those are the four agonists we used. They were all high efficiency agonists, either 54 or 51%. And the side chains we turned the G into were shown in the inset there. They were into serine, alanine, proline, and lysine. And the serine mutation is a congenital myasthenic mutation in humans. So for all of these high efficiency ligands, the resultant efficiency after the mutation was 42%. You can see by the green arrows where the starting efficiencies were, and you can see the histogram that the mean was at 42%, which is the resultant after the mutation. There was one that was about 32%, which was nicotine on G153K. That's shown at the very far right in the inset. So we know these numbers. These numbers are familiar: 55%, 51%, 42%, 35%. We have seen these numbers in wild-type receptors: 55% for TMA-type ligands, 51% for ACH-type ligands, 42% for epibatidine-type ligands, and 35% for varenicline on wild-type binding sites. So these mutants appear to change efficiency in a modal way. So in addition to being discrete and precise, I think it appears that the resultant efficiencies following mutations are modal. So the binding site is only capable of producing certain efficiencies, is what our hypothesis is, that the binding sites adopt discrete structures that correlate with efficiency. That is, it's not a rubber room that the binding site wants to click to an O conformation, but if it's frustrated by van der Waals or other forces, it goes to a different alternative structure that's discrete. And it doesn't go to 70% efficiency, or it doesn't go to 25% efficiency. It's like a spectrum, so that the efficiency map of a binding site is sort of like a spectrum or a barcode of that binding site, is our hypothesis. And of course, to confirm this, we need to measure many more agonists. Another hypothesis we draw from this is that mutations that change N mark the conformational change pathway. This is a little more speculative, but the fact that the mutations of Y198 over on the left don't do anything makes us think that it's not really involved in transferring binding energy into gating energy. It's not launching energy into the gating machine, whereas Y190 and 149 would be. And of course, this needs to be tested by making more mutations further and further away from the binding site. See what the pattern is with mutations. So I hope I have convinced you that efficiency can be used to probe activation mechanisms. If any of those hypotheses that we proposed turn out to be true, they were derived from an analysis of efficiency. But in the next 2 slides, I'm going to show you how efficiency can be used to facilitate a concentration response curve analysis. And the key here is the blue equation, which relates the gating equilibrium constant, Ln, n being the number of binding sites, and the low affinity binding dissociation constant, KDC. And those two are related only if you know m and log 0. M is the slope of the efficiency plot, which is related to efficiency, and log 0, of course, is just the unliganded gating equilibrium constant. So if you know those 2 parameters, you can calculate affinity from efficacy and efficacy from affinity using this blue equation. So you may be saying, well, I don't know those 2 parameters, so what good does it do me? And I think that in the long run, those are the 2 parameters that you need to know. If you listen to my first video, you know I'm in love with L0, and that to me is the hallmark of a receptor. It's the first thing and most important thing you can learn about a receptor is what nature has given you for the energy difference between C and O without any ligand. That's the baseline from which everything happens. So that's a very important one to know for receptors. And as I go further and further in efficiency, I think efficiency is the first thing you want to know about an agonist. If you know its efficiency, then KD, its affinity and efficacy are related by efficiency. So efficiency is the thing you want to know about an agonist. The first thing I want to know about an agonist is what's its efficiency. So if you show me a receptor, I'm going to ask you what's L0, and if you show me a ligand, I'm going to ask you what's its efficiency on that receptor. So if you know efficiency and L0, you can calculate efficacy from affinity, and L0 applies to all agonists. It is one and done. So these are reasons why I think someday we will know much more about L0 and efficiency. These are early days. So once you know L0, you're done with it. There's many ways to measure it. It takes a little bit of work, but it's definitely worth it. You get that number, you know it, it's for all time. And efficiency applies to many agonists, as I showed you. They belong to an entire family of agonists, and it can be predicted from structure probably. There's a proviso for that. So I'm showing a picture of nicotine down below, and to the right would be a derivative of nicotine. And if nicotine is 51%, I think there's a good chance that these derivatives of nicotine would also be 51%. So you can put a chloride or a fluorine or a methyl group or whatever you want for that R. It's still going to be 51%. It may have very different affinity and efficacy, but you will know a priori that ligand is 51%. This will take time to prove, and particularly you need to know, you may be even be able to prove it with structures as you know more about the binding sites. But so I think that going down the road, L0 and N are going to become increasingly important for understanding agonist action. So I'm going to show this now in the form of dose response curve. So given efficiency and L0, a CRC can be calculated from only the maximum response. So these are wholesale dose response curves that I showed previously. I've added carbachol to the story here. And we can the circled points are the maximum values, and we took the maximum values, just one concentration. We use those concentrations, the responses at those concentrations, to calculate L2, and then that blue equation, given the efficiency now of 50%, we use 50% for all of these because we were trying to say, what if you really didn't know your efficiency and you just sort of took a number? So it's average of 50%, even though TMA is higher. And you can see On the right, we calculated the entire dose response curve from just that maxima, from these maxima, and you can see you get a pretty good fit. Okay, ACH is off a little bit, maybe because of desensitizations, lowering the maximum. TMA is off a little bit because of it's 54% instead of 50%, but both the epibadidine and the carbachol points are very well fit. So EC50 can be estimated from the response to just one agonist concentration. This seems to me to facilitate dose response curves if you only had to measure the response at one concentration in order to calculate the whole curve. And similarly, because of the blue equation, you can, given efficiency in L0, a CRC can be calculated from only the EC50. So here are the EC50s. What we did, we took those curves and normalized them to a maximum of 1. So in all cases, their maximum is 1. And we just fit them to the Hill equation to get just the EC50. This is how many studies are done, by normalizing the response. So we have 4 AC50s, and given efficiency, again, of 50%, we were able to calculate the curves shown to the right. So the TMA curve, all the curves fit well, pretty well, except for the TMA curve, and that one fit much better when we use the real efficiency of 55%. It's very sensitive to the efficiency measurement. In fact, this could be one way to measure efficiency, is by finding what efficiency is required to make this transition here. But efficacy can be covered from a normalized CRC. So this can be done on published literature values. If you know the efficiency of your ligand and L0, you can recover the maximum even though you've normalized the curves. So that's the end of the second chapter on efficiency, where I described the measurement, definition, features, structures, and applications. And to the right are shown the people who contributed to this work. And at the end of the third video, I will go into the acknowledgments in more detail. But the third video is going to be about the energy linkages that undergird the correlation between affinity and efficacy.